You guys had a week off, so I'm sure you've kind of coalesced all that data in your head, and you kind of have a really firm grasp of confidence intervals and all that fun stuff. Okay, so I think now that we've kind of got a lot of the basics down, talking about variability, talking about means and medians and all that good stuff, all the kind of foundational stuff, this stuff will come a little bit easier to you, I hope, when we start to talk about things like p-values and statistical significance. So again, this is what we're going to go over today. And so some of the objectives we're going to look at, including understanding p-values and how they're calculated. We'll ask you to actually calculate them, but at least be able to see where that information is coming from. We'll talk about one-tailed and two-tailed p-values and what that means. Relationships between p-values and confidence intervals. Understanding significance of a confidence interval, including or excluding the null hypothesis. So the null hypothesis is going to be a really important definition we'll talk about, and it's really going to be good for you guys to be able to identify if I were to give you some sort of scenario, what the null hypothesis would be, and then what rejecting that would mean. So we'll talk about that as we get to it. We'll look at things like interpreting results that are or are not statistically significant, and start to distinguish things like statistical significance from scientific importance or clinical significance, because oftentimes those are very different. And then we'll look at statistical power, and then the concept of equivalent zones. Okay, so talking about p-values first. And so even though we probably rejected the null hypothesis years ago, it still rears its ugly head. You still need to know how to reject it, right? This will be funnier later when you know all this. Guaranteed. Okay, so defining a p-value. So essentially, let's take the scenario of flipping a coin again, right? Because we know that in general, as long as you have a fair coin, you should have a 50-50 chance of getting heads or tails, correct? Right, so if I did this example 1,000 times, I should be able to get a distribution that looks like a pretty normal bell-shaped curve of my results here. And now if I were to flip a coin 20 times and I were to find that I got 16 heads and 4 tails, how unlikely is that, right? So what are the chances that I would end up getting 16 heads and 4 tails, knowing that the average should be 50-50, okay? And so this is what the p-value is going to help us determine when we're looking at this. So again, the assumption is, and this is going to go back to what our null hypothesis is that the assumption is that as long as it's a fair coin, as long as we're having normal randomness in the data, we should be getting a 50-50 distribution of heads and tails, right? So expecting it to be fair, the null hypothesis should be true. So then what we need to do is defining that the null hypothesis is basically just saying that there is no difference between what we're testing versus either the population mean or whatever comparator group we have. So say for instance, we were comparing patients who had a polymorphism in one of their enzymes, and we're looking at metabolism of a drug. The null hypothesis would be saying that compared to the general population, that this group would have no difference in metabolism of a drug versus if that polymorphism actually did have a significant difference, you would end up seeing there being a large difference there between the two populations, right? The sample and the population. So basically the null hypothesis just says there's no difference between the two groups, okay? So basically we're going to say, with flipping a coin, we know this is going to have a binomial distribution because, again, if we're looking at it, we're just going to have either heads or tails. So there's not really kind of a continuous variable here. It's going to be one of these nominal dichotomous variables that we're looking at. And so basically what we're going to say is that if we were to run this experiment, what are the chances are that we would get looking at getting 16 heads or 4 tails? And basically what you end up seeing, if you looked at the normal distribution, that your chances of that happening would be 1.19%. Okay, so say we did the math, we end up getting a result that says that 1.19% of the time that you were to flip the coin 20 times, you should be getting 16 heads and 4 tails. Okay, so pretty unlikely, right? So this, in this case, would be determined to be the p-value. And then very frequently how you'll see it also being defined would be in the decimal point value. So in this case, 1.19% would basically be 0.0119. So again, frequently you'll see p-values being expressed like that. And so essentially what we're saying is that the p-value answers kind of a generic question. It says, if the null hypothesis were true, being that the distribution should be 50-50, what is the chance that we should observe a result as extreme as this or more extreme in this particular experiment, right? And so if I were to run this experiment, the chances are of just getting a result that's this extreme is 1.19%. So again, fairly unlikely. And in general, when we're looking at statistical significance when it comes to the medical literature, p-value of 0.05, or otherwise known as what percentage?
5%.
Yeah, 5% would be considered to be the cutoff for statistical significance, right? So basically it's saying that, if I were to reach a p-value of 0.05, it's saying that just by random chance, I would get a result that is that or more in 5% of the time, right? So again, you know that for the most part, like this result is unlikely to occur by chance alone. Again, so looking at the null hypothesis, again, just telling us that there's no difference between either the population parameters in our sample that we're looking at, or if we have two different samples, say we're doing drug testing to look to see which drug has a better effect on blood pressure, the null hypothesis would be that the change in blood pressure would be the same between the two groups, right? So no difference that's there. And then the p-value is going to be that numeric representation that shows us the degree of the chances of getting a result like that and how large or small those chances are. And so very frequently we're using p-values to tell us whether or not we've achieved statistical significance, and usually it's based on a preset definition of 0.05, or if the researchers decide to set a different one, say 0.01, that's another common one you may be setting as statistical significance. So basically the thing that it comes down to is that the smaller the p-value is, the smaller the chance that just random variation caused the results that we're seeing in a test, right? So if I have a very large p-value, it would tell us that, if it's something like 0.8, which would be 80%, it says that this result could have happened 80% of the time. So that's not anything. It's not a very surprising result. When you have very small p-values, it's saying that those results have a very small chance to actually be due to random sampling. It's going to actually be due to some difference that there is between your sample and your population. Does that make sense? So small p-values mean that random chance is very unlikely to have been a result of the results that you got, that there actually is something going on there, some difference between your group and your population. So again, when we're doing hypothesis testing, that p-value is the probability of obtaining a test statistic at least as extreme or as the one that's observed, assuming that the null hypothesis is true. So that's kind of the thing you have to go back to in looking at. Very frequently, we're looking to see whether or not we're going to be rejecting this null hypothesis. And so when you have results that come back statistically significant, say the result comes back 0.01, so 1% chance that random sampling caused this result, you would say that, okay, we are rejecting the null hypothesis. We're rejecting the fact that there is no difference between these groups and that there is some sort of difference between the two. Okay. Again, very frequent, 0.05 is typically going to be set as your value. And when you have a level of significance set, this is often your alpha value. So if you ever see the Greek alpha symbol, or you hear alpha being talked about, this is usually what the researchers are setting at as their level of statistical significance, right? So if I have an alpha of 0.05, that means that I have to achieve a p-value of 5% or less in order to achieve statistical significance. If I set my alpha at 0.01, that means I need to achieve a p-value less than 1%, right? Otherwise, I'm saying that the chances that the result that I have are just too likely to be due to random sampling to say that there's a difference and to reject the null hypothesis. Everyone with me so far? Perfect. Because it's really critical to understanding what it means when someone says, oh, this is statistically significant. What does that really mean to you guys? We'll see with some examples when we're going to be looking at this. So again, when you're able to reject the null hypothesis, that means the results are statistically significant. So now, like we mentioned, that when you set the alpha error or your alpha rate, that's again something you're setting a priori, or something you're setting prior to running the actual experiment. And so most researchers, when you're reading a journal, should be able to point out what their alpha level is prior to saying what the actual results are. And before they run the experiment, they should set that value to whether it be 0.05 or 0.01. Now, when we're talking about different types of errors that can be made and whether or not our results are statistically significant, we're going to talk about type 1 errors and type 2 errors. Okay, so a type 1 error is basically going to be referring to us incorrectly rejecting the true null hypothesis. So basically saying that there is a difference here when there really is no difference between the groups. Okay, so this would be a false positive, would be another term for this. Okay, so that's a type 1 error. So if I were to say, for instance, I were to take a random sampling of people and I were to take just a subset of them out and were to say, to run some sort of experiment, and I were to say, yep, these guys are definitely different than the population, when that's not actually true. That would be a type 1 error. And so if I were to set my alpha level at 0.05, kind kind of what are my chances of making a type 1 error?
1 in 20?
Yeah, 1 in 20 basically. So I'm saying that when I set that alpha level at 0.05, I'm saying that there's a 5% chance that these results could be due to just random sampling. So I'm basically saying 1 in 20 would be a false positive. Okay, so then when I go say, if I were to set that alpha level to 0.01, then at that point, how often am I going to get a false positive? My results come back less than 1%.
1% of the time.
Should be like 1 in 100, right? So again, if you're looking at things, typically, if you would like to make it so that you're less likely to find a type 1 error, you set your significance level lower, right? You set your alpha lower. So that way, if you were to get a result that came back and say, my alpha is 0.01, and I had a result that came back, p-value, at 0.03, would that be statistically significant? No, because I set my alpha at 0.01, and so now I have a p-value that's greater than that, which would mean that it's not statistically significant. Okay, the chance of making a type 1 error is too high at that point.
So when it's not when it is statistically significant, then there's no difference between the group and the population.
No, okay. So again, going back to this, so if I have a result that is statistically significant, meaning that it has the p-value is less than my alpha. Right, so I set my alpha at 0.05, and I get a p-value that says less than 0.00001, right? So a very, very small p-value. That's saying that that is statistically significant, that there is a difference between my groups, and I reject that null hypothesis, right? Yes?
What makes you set your alpha, like what decides where you set your alpha?
It's a good question. So traditionally, 0.05 has just been what people have set it at, right? So I don't know the full historical context on how that got set, but that's kind of what it is. Now, if you would like to make your results less likely to show a type 1 error, then you set your alpha value lower. And we'll actually see in some cases where we talk about multiple comparisons how sometimes when you're doing multiple sets of analyses, you'll actually use that 0.05 as your total level of significance for the whole group. So basically none of them can equal greater than that 0.05, but we'll talk about that a little bit later. Just know that your results are going to be a little bit less likely to show a type 1 error if you set your significance level lower. Okay, and then the flip side of that would be a type 2 error. So this would be if you were to say that I'm going to say that there is no difference between these groups, that I retain the null hypothesis, but there actually was a difference. Okay, so that would be a type 2 error or a false negative. Okay, very frequently type 2 errors come about from having too small a sample size to actually show a true difference. We'll talk about power calculations a little bit later, but type 2 errors and power are intrinsically related to one another. So when power comes up a little bit later, just refer back to this type 2 error. Okay. So type 1 errors would be a false positive in which you say that there is a true difference between these groups, and you reject the null hypothesis when you actually should not have done that. There was no difference between the groups. And then type 2 errors are going to be when you say that there's no difference between the groups, but there actually is. Okay? This will make more sense when we actually look at some actual clinical corollaries. Okay, so the p-value, looking at this, some of the things to remember, just because someone says something is statistically significant, you should never just take them at face value for that. You should always really investigate what that p-value is telling you. P-value does not actually tell you anything about the size of the observed effect, okay? So just because I have, say I'm looking at different blood pressure treatments, and I have a 1 degree drop in blood pressure that is statistically significant, does that really do anything for you? Not really, because right, 1 millimeter mercury difference in blood pressure is not really going to make or break anyone, right? So just because the p-value is very significant does not mean that the results are actually has anything to do with the actual effect size that you're seeing there. And so what you can actually see is that, again, going back to sample size, right? Because the larger our sample size does what to the variability of the data? Increased sample size, variability goes up or down? Should go down, right? Because I'm more closely approximating that population, right? If I'm looking at normal distribution of a sample. So if I have a small study where I only maybe have, say, 30 participants in it, and I were to have a very large dramatic effect, it's going to be easier to get a significant p-value. And on the other hand, if I were to have a very small effect that's occurring in a very large population, so say I was looking at 1,000 participants in a study, it's going to be easier to detect a very small effect. So just keep in mind that just because the p-value is significant does not mean that it actually refers anything back to the real effect size that you're looking at. Okay. And so then the other thing to look at as well is that the more variables or endpoints that we're looking at, so if I look at, say, I give patients, I do a randomized controlled trial where I randomize patients either receiving, say, simvastatin or no placebo. If I were to run that study and I were to look at things like cardiovascular death, I look at all-cause mortality, I look at inflammation markers, the more endpoints that I have, the more things that I'm comparing, the more likely I am to run into these multiple comparison errors, and the more likely you are to make a type 1 error. And again, so type 1 errors are going to be a false positive or false negative? False positive, right? So I'm seeing results that look like they're statistically significant when really they're not. It's just because I kept testing it over and over and over again to end up finally getting some significant results. And so I'll show you kind of how when you do multiple comparisons, that risk gets higher and higher as you go in just a little bit. Okay, so again, just to put it in kind of graphical representation, if we're looking at a normal distributed sample here, right? So again, a normal bell curve, this could be considered a Gaussian normal distribution of values. And so basically we're just saying that looking at our p-value, it's just telling us how kind of extreme of a value that we're getting with the chances of that actually occurring. And so typically you're looking at values that are kind of lying away from the actual mean. And so if I'm here in this kind of area here, kind of in the middle, because we know that samples tend to regress back to the population mean as you start to increase your size. That it's random chance can be responsible for a lot of results, but as you kind of get farther and farther away from that mean, you can start to see that the chances of those values occurring are going to become less and less likely. And so that's what our p-values are really telling us, is that what are the chances that just random sampling could have produced these kind of values. And so the smaller that chance is, the more likely we can say that there is a statistically significant difference between these groups, and I can reject that null hypothesis. Everyone with me? So again, looking at just another way of kind of evaluating this. So again, we'll say up here, and very frequently the null hypothesis is marked as H sub 0. So you can see here that on the top you have if the null hypothesis were true, and if the null hypothesis was false, and then whether or not we're rejecting or not rejecting the null hypothesis. So in the case that the null hypothesis is true, and that there is no difference between the groups, and I were to reject that null hypothesis, that's a type 1 error, right? So that's a false positive at that point, right? Because we know that there's no difference between the groups, but we're rejecting it anyway, okay? So that could occur if we were to do multiple comparisons, or we just kept looking at different things to try to find significance that can come up from that cause. Now on the other hand, if the null hypothesis was actually false and I were to reject it, that would be a correct decision, right? Because I'm actually finding a statistically significant result showing that yes, I can safely reject this null hypothesis. And then on the other hand, if I were to have a true null hypothesis and I were to not reject it, then that would be a correct decision, right? On the other hand, if I were to not reject a false null hypothesis, so saying that there is a difference between the groups, but I do not reject the null hypothesis, that's a type 2 error. So that's going to be a false negative, right? That makes sense to people? And again, when you're actually performing the studies, do you ever really know whether or not your null hypothesis is true or false? You don't, right? You really can't. Depending, at least in the kind of biomedical literature that we're going to be focusing on, you never know what the actual null hypothesis, if it's true or not. And we'll kind of look at an example of that in a minute. But basically, by using things like our alpha levels and looking at power calculations, we're basically telling us what our chances are of getting one of these type 1 or type 2 errors. And so by setting it at kind of predefined levels, you kind of set yourself and say, okay, I know that random chance may be responsible for at least 5% of these results, but that's good enough for me, okay? Okay, so going back to our examples, you guys remember that body temperature examples we were looking at where you had both a subset of, say, like 130 patients, then we had 12 patients, a subset of that, and we're evaluating body temperature for them. So again, going back to that, let's look at what our null hypothesis is. And so if we say that normal body temperature, in this case, has been hypothesized to be 37 degrees Celsius, what would be your null hypothesis? So if I were to take that 130 patients and I were to evaluate their body temperature, what should that mean be?
The mean should be 37.
should be 37, right? Because I'm saying that there's no difference between the groups. So it doesn't matter what subsample of patients I take, I should be able to pull them out, and I should get a mean that kind of regresses back to that 37 degrees Celsius. Okay, so that would be the null hypothesis. There's no difference in body temperatures between those two groups, between the population and the sample that I'm looking at. So if we were to actually look at the data that they had, we saw that their actual mean temperature from the 130, the N of 130, was 36.82. Okay, so not a big difference there. And when you look at the confidence interval, right, the 95% confidence interval, it ranged anywhere between 36.75 up to 36.89. And so is that a very wide variation in confidence intervals? No. And remember, as your sample size gets bigger, your confidence intervals do what?
Small.
It gets smaller, right? Because I have a better idea that I'm 95% sure that the true value lies somewhere within that range, right? And so as I get a bigger sample size, that confidence interval is going to shrink, and so I can be more sure, and I can have a much more narrow range of numbers to say, yep, the true value is somewhere within there. So, but notice here that the 95% confidence interval does not include 37 degrees centigrade. Okay, so when you're evaluating this, and notice that at this point I don't even need a p-value to tell me that these results are statistically significant. And I'll show you how you can evaluate that in just a second. But based on this, based on the fact that the 95% confidence interval does not include the population mean of 37, I can say that these results are going to be statistically significant. So I can say, at that point, do I reject my null hypothesis or do I keep it? I would reject it. So I'm going to say, yes, there is an actual difference here based on the hypothesis that the population mean body temperature is 37 degrees centigrade. So again, looking at this, the discrepancy between the sample mean and then the hypothetical population was 0.18 degrees centigrade. And when you actually, the p-value basically says, the value that the p-value tells you is that if the population mean is truly 37 degrees centigrade, what's the chance that a sample of, sample size of 130 patients, you would have a value that differs from the mean by 0.18 degrees centigrade or larger. And so if you're actually able to get the p-value and calculate that out, you get a value that's 0.00000018. Okay, so what are the chances of that actually occurring? Very, very small, right? So they're saying that yes, there actually is a statistically significant difference between the sample that I have and my hypothetical population mean, right? So this means that there's a very tiny chance this is just due to random sampling, and there actually is a true difference between my hypothesis and what I'm actually measuring. So again, p-values should always be interpreted within context here. And again, going back to my hypothetical or my hypothesis, was that actually, should I have set the population mean at 37 degrees centigrade? What kind of data am I going off of when I'm looking at that? So that's really important to go back and say, like, okay, well, what's the population mean that I was really looking at? Where am I pulling that data from to see what that was in the first case? So. So again, very frequently when you look at like normal values for like lab values and things like that, you're going to see that it's usually based on tradition, and very frequently, a lot of those kind of preset things on what a normal serum sodium is or normal body temperature. Usually it's just set on tradition, not really on overwhelming amount of clinical data. So again, looking back at this, you could probably say that your null hypothesis was probably kind of a bad one to start with because the actual population mean probably wasn't 37 degrees in the first place. Right? So again, this isn't really rocket science here telling us anything brand new, but again, always go back to your assumptions at the very beginning to make sure that those are going to be accurate. So if I were to look at the subset of those 12 patients again, and I were to see what their mean value was, and I was looking at their 95% confidence interval, what do you notice about this confidence interval here with the 12 patients versus the 130? Yeah, it's much wider, right? So the confidence interval is much wider because I have a much smaller set of patients that I'm looking at. And so if you were to look here, you see the p-value is 0.0687. So is that statistically significant? So if I set my alpha at 0.05, yeah, no, at that point, because the p-value is greater than the 0.05 that I set it, so that means it's not statistically significant. And if you look at this, if you notice that the 95% confidence interval actually overlaps what that null hypothesis mean was of 37 degrees centigrade. So I'll show you a graph in a second that makes that a little bit more clear, but just notice because it actually encapsulates that population mean, that's what's helping it to make it not statistically significant. So again, what can we say about the differences between the large and the small study? Obviously, the more patients that we have, the larger the value of n, the smaller that standard error of the mean is going to be, and it's going to allow the confidence intervals to be more narrow. Okay. There's also this concept of whether or not you want to look at one-tailed versus two-tailed p-values. Anyone, can they think of what a tail might be referring to?
The ends of the curve, the bell curve.
Exactly. Yeah. So either end of the bell curve that we're looking at. So you'll frequently hear people talk about whether or not they're going to use a one-tailed p-test or a two-tailed p-value. If you ever see, one-sided or two-sided, that's basically referring to the same thing. So basically, if you imagine that you're comparing the mean of two different groups, essentially what you're seeing here is that the one-tailed t-tests, or the one-tailed p-values, are saying that you already are making an assumption about which group is going to have the larger mean, right? So you're kind of making some assumptions about which direction your values are going to go. So if you imagine, if I were to give patients, or to do a randomized controlled trial, and I were to compare a group that were receiving antihypertensive and one that were receiving placebo, which one do you think would have a lower blood pressure? Probably the one getting antihypertensive, right? So you wouldn't expect the people in the antihypertensive group to have a bigger blood pressure, right? To have a larger change in blood pressure, right? So because of that, you can kind of assume which direction those results are going to go. And so I can look at using a one-tailed p-test, or one-tailed p-value versus using a two-tailed. Now, if I, for instance, we're looking at something that I can't make an assumption on which direction things are going to go. So if I were to look at, say, drinking 1 glass of red wine a day versus drinking water, what's that's going to do to your blood pressure? I have no idea, right? Could raise it, could lower it. In that case, because I don't know which direction it's going to go, I want to make sure that I don't increase my chance of making a type 1 error, and so I use a two-tailed test, right? So basically, by looking at your null hypothesis and being able to, whether or not you can kind of make an assumption on which direction the values are going to go, or which group is going to have a larger mean, you typically want to go with a two-tailed test, versus if I know and I can make an assumption on which group has a larger mean, or will have the larger mean, then I would go with the one-tailed test. So if you're looking at this, obviously, which one do you think would be easier to achieve significance with, statistical significance? If you imagine this this graph, we are imagining percentages on either side. If I'm going with the one-tailed test, basically I can say that any 5% within this group would be considered statistically significant, right? If I go with a two-tailed test, though, I'm basically having this and saying, okay, I need to get a value within the 2.5% mark here, or in the 2.5% here, right? So the p is still, the alpha level is still 0.05, but it just gets divided between either side of that curve. That make sense? So if you had to imagine which one is it easier to get statistical significance with? Yeah, one tail, right? Because your window is a little bit bigger on that one side, right? So that's what we would say, that the two-tailed test is going to be more robust. It's less likely to be making false type 1 errors, right? Or rejecting the null hypothesis incorrectly. So kind of go back to that. If you can make an assumption about which group is going to have the larger mean, you can get away with using a one-tailed test. Versus if you are not sure, you go with a two-tailed. The one-tailed is going to be more likely to produce a type 1 error. But if you already have an idea where the values are going to go anyway, that's okay, right? Because you want to be able to make sure you can actually hit that significance level. So again, just going back to this, just know that kind of what we already talked about, that the two-tailed test does not assume which group will have a greater mean. It's harder to achieve statistical significance, but you're also less likely to make one of those type 1 errors. Okay. Now, say for instance, I had a group, say I was going back to that antihypertensive example, and I were to run the results as a two-tailed test. What does that increase my chances of making? Type 1 error or type 2 error? Type 2 error, right? Because I'm more likely to, because I'm kind of placing harder restrictions on the values that are going to achieve statistical significance, I'm more likely to get results that are not statistically significant. And even though there might have been a difference there, I might not be able to show with the results that I have. So you're more likely to make a type 2 error or to incorrectly retain the null hypothesis, right? So, and very frequently, if you are not really sure what to do, what should you go with, one-tailed or two-tailed? Right, so why would I go with a two-tailed?
Because it covers both ends.
Covers both ends. But also, the other thing is in science, would you rather make a type 1 error or a type 2 error?
Type 2.
Why would you rather make a type 2 error?
Because it keeps things the same.
Right, so basically it doesn't really change anything. If I make an incorrect error, if I make a type 1 error and reject a null hypothesis, that's telling you that, hey, there's something here when really there's nothing. And so sometimes people can run with that and make bad clinical decisions based on those kind of results. So in general, you'd rather make a type 2 error and incorrectly retain the null hypothesis versus making a type 1 error. Okay, just in general. So again, a lot of times, even if you're not sure of whether or not your data is normally distributed and things like that, you typically try to go with the more the harsh test, the more difficult test to pass in order to avoid making a type 1 error. So that's kind of a general rule of thumb. Okay, so we kind of talked about this already. So when is it appropriate to use a one-sided p-value? Again, if you know which one is going to have a larger mean just based on common sense, based on physical limitations, whatever it happens to be, or even previous data. If you're trying to replicate results of another study, and you know kind of which way the direction the values are going to go in, that's okay to use a one-sided test at that point. But again, if you cannot predict which way the direction the values are going to go, you really should be using the two-tailed test. The other thing is if you were to use a one-tailed test, so say in the group with the receiving the antihypertensives versus placebo, if I were to have the antihypertensive group come back with a larger mean blood pressure than the group that received nothing, even if that result ended up being less than 0.05 because it kind of went the wrong direction, I would still say that's not statistically significant. The data doesn't really make sense. We need to repeat it or do something. At that point, you just throw those results out. Okay, so here's an example of a one-tailed p-value. So say we're going to be testing whether or not a new antibiotic is going to impair renal function. And we're going to be doing that by measuring serum creatinine. Okay, so we know that lots of different antibiotics can damage kidney cells, resulting in reduced GFR, increased serum creatinine, right? So there's no known antibiotics so far that were known to decrease serum creatinine or increase GFR, right? So if anything, it's going to hurt kidney function. It's never going to necessarily help kidney function. So at this point, before collecting any of the data, you can say there are two possibilities, right? One, that the drug will not change the serum creatinine of the population, which is that our null hypothesis, or not.
Is the null hypothesis.
Right, so that should be the null hypothesis, saying there's going to be no change between the people getting the new antibiotic and the people not receiving it, right? And then our actual thing that we're looking for is that whether the drug will increase the mean serum creatinine in this population, right? So at this point, you'd be considering it impossible for it to decrease the serum creatinine, so there's no point in using a two-tailed test. I would just be more likely to make a type 2 error that's kind of not necessary. I can use a one-tailed test and be more likely to actually achieve that significance and be more likely to show a true difference if there is one there, right? Does that make sense for why I would use a one-tail versus a two-tail? Okay. So again, if it makes sense to calculate a one-tailed test, for this case, you'd be more likely to make a type 2 error if you were to go with a two-tailed test, so that's why we're avoiding that there. And again, very frequently, if you're not sure, just use a two-tailed test because you'd rather make a type 2 error than a type 1. Okay. So again, when looking at the reason why two-tailed p-values are used more often than one-tail, again, kind of the reasons we already stated here. But again, the fact that they're more conservative is usually the frequent reason stated for that. It's just the fact that you're less likely to make to say that there is a true difference if there's not one there. So just more easily, or less chance to actually make a type 1 error at that point. And then also if you're comparing multiple groups together, so say you're doing more than just two comparator groups, it doesn't make sense to have a three-tailed test, right? So that doesn't really make any sense. So in those cases, by using a two-tailed test, you kind of achieve very similar values, and so you're, again, less likely to make one of those type 1 errors. Okay. Okay, so now we have an idea what p-values are, how we're going to use them. We can look at statistical significance in regards to hypothesis testing. Okay, it's always good to have an educated guest when you're looking at hypothesis, right? See, these get funnier as you go along, right? Not really. Okay, so when we're looking at statistical hypothesis testing, this is helping us to automate decision making following these steps, right? So these are the things you need to do prior to running any type of data, collecting anything. You need to set these values up beforehand in order to make sure that your actual values are valid, right? You don't want to change things on the fly because that's going to introduce bias and be more likely to make incorrect conclusions. So one thing you want to do is to define your threshold p-value, so that's your alpha. Right? So typically either 0.05 or 0.01, that's really going to be telling you what you're going to consider to be significant or not. So again, if you are testing, if your results come back and the p-value is less than your alpha, then you would conclude that the test is, the results are statistically significant and you reject the null hypothesis. Otherwise, you're going to retain the null hypothesis, saying there's no difference between the groups. So basically, this is just saying that we're going to assume have this presumption of innocence until proven guilty, right? So we're going to be saying that the null hypothesis is true until proven otherwise. Okay, that's always going to be your assumption when you're going into research. So, for instance, like when I did my research during my fellowship, we were looking at coral snake bites. We were looking at the shortage of coral snake antivenom that occurred basically in the mid 2000s. And so we're looking at results between patients who had easy access to the antivenom and patients who had limited access to the antivenom, and how the results change, right? And so, in that case, what would be my null hypothesis? Yeah, there's no difference, that your outcomes are going to be the same. The same proportion of people are going to be intubated, same proportion of people are going to have the same kind of outcomes. And then in order to reject that, it would have to have results that show statistical significance to say that these patients are going to have better outcomes or worse outcomes, whatever it happens to be. So again, the assumption is that there's no difference between groups going into it until I have the actual data to support rejecting that null hypothesis by having a result that is statistically significant. Okay. And again, just because we say that we are rejecting or accepting the null hypothesis does not inherently mean that the null hypothesis is true, because sometimes you can go in with bad assumptions, right? Looking back at that data with the population saying that the mean population temperature is 37 degrees centigrade, it's probably not that exactly, so doesn't mean that that's true. It just means that we either reject or accept the null hypothesis in regards to the difference between groups. Okay. Again, sometimes you'll see hypothesis testing used in quality control. Rarely you see it used in exploratory research. And basically, just because you find a value that is statistically significant does not necessarily mean that you should, start changing your clinical practice on things, right? Sometimes it is, it's more important to evaluate the confidence intervals to have a better idea of specifically what kind of takeaways you can get from the data that you're looking at. So again, always go back and look at the data and not necessarily the conclusion that the authors are going to be providing you when evaluating the stuff, right? Because they can say, hey, this change in blood pressure was statistically significant, but you go back and look at the data and find that it's a very, very weak, very weak conclusion they're making based on the type of p-value they got and based on the actual confidence intervals you're looking at. We'll kind of go into more detail on that as we go forward. But just remember to look at the data and evaluate it on itself, and not just look to say like, okay, this is statistically significant. So again, just to kind of give an example of this, is something that's has a p-value of 0.004 more statistically significant than 0.04? Is one inherently better?
Some say no.
Some say no. But in reality, what is this just telling us? What's the difference here between the 0.004 and 0.04? Basically, it's saying that if you are, which one are you more sure or has a less chance to be just due to random sampling? The smaller one, right? So this is just telling me that the possibility of this being due to just random sampling or random error is much less than the 0.004, right? It's only 0.4% versus something that is 4%, right? So it's just telling you your probability of getting a value this extreme or more so in a value that is, or in data that's being pulled from a random sample. So again, some people I would probably end up in the camp saying no, that once you achieve statistical significance, you're kind of done. So whatever your value is, if you say your alpha 0.05, anything less than that is statistically significant. I don't really care what it is after that, because sometimes in journals you'll see them say 0.00000018, and it's like they're just using up too much ink at that point. So very frequently you'll see them just put less than 0.01 or less than 0.001, just to kind of show you that it's a very, very small p-value, and it's very, very unlikely to be due to random chance, and more likely to be due to an actual difference between the groups. So, so again, sometimes people use kind of this kind of Michelin guide scale. You guys have heard of the Michelin star scales? What does that do? What does it rate?
Restaurants.
Yeah, rates restaurants. So you get 1 star, 2 star, 3 stars is kind of the best. So if you look at this, you can say, p-value of greater than 0.05 you can consider not significant. So if you see NS, that's frequently that's referring to. And then you can kind of have higher degrees of significance. I usually don't see the stars being used, but very frequently you'll see things like p less than 0.01 or p less than 0.001, just to show that it's a very small p-value and very unlikely to be due to random chance. So again, now what if something is kind of borderline statistical significance? So what if you had a p-value that was 0.049? Do you get a lot of difference in regards to if you had one that was 0.051? What do you do with that? Yeah, so frequently what people will say, if you have a value that is very close to achieving significance but not quite, let's say it's trending towards significance, right? So it's basically saying that you did not achieve your value, so you can't say it's statistically significant, but it still could be telling you something, right? So maybe if I resampled and did a whole new experiment testing the same thing, I could find significance there, right? So it still kind of gives you a clue. It's just you can't say that it's statistically significant based on whatever your alpha value you set at. So again, it's probably better just to look at the data and see kind of where things are at when evaluating the stuff, and not just look at a p-value. Okay, so again, when we're choosing our significance level, usually it's at 0.05. Again, we said it's kind of just due to historical precedence, not really any kind of rhyme or reason I know of, at least. But your chances of making a type 1 error are going to be higher as you set your significance level lower. Right? So as it gets more and more difficult to achieve statistical significance, like going from 0.05 to 0.01, your chances of making a type 1 error are going to go up or down. So it should go down. Sorry if I misstated a second ago. So as you decrease your p-value or your alpha, you make it more difficult to achieve statistical significance, your chance of making a false positive are going to go down. Right? So type 1 errors go down as you set that lower, but that increases your chance of making what?
Type 2 error.
Yeah, type 2 error. So again, as you, they're kind of on a seesaw where as you decrease risk of making type 1 errors, you're increasing risk of making type 2 errors just because it's more difficult to achieve that significance, and vice versa. If I were to raise my p-value up to 0.1, that's going to be very easy to detect statistical significance between groups because, again, I have a 10% chance of finding something just due to random chance, right? Again, that's going to be the same problem we run into when we look at multiple comparisons a little bit later. So again, and even looking at 0.05, that still means we have a 1 in 20 chance of finding something results that are just due to random error. So just keep that in mind, and just realize that there is a slight difference between the alpha and the p-values that we're looking at. The alpha is something we're presetting as our level of significance, and then the p-value is actually what the data is showing us. It's just showing us the actual chances of getting those results due to random chance alone. So even though if I were to run the same experiment multiple times, I'm going to keep the same alpha every time, but the p-values could change based on the data that I'm getting back. Okay, it's important to realize the difference there. Okay, so then we will look at the differences between confidence intervals and statistical significance when we come back from break in 10 minutes. Any questions from before the break? Okay, you guys are p-valued out, I can tell. So we'll continue on as we go talking about confidence intervals and how they are going to be really tied in with the p-value. So again, we know that confidence intervals are computing that range that you can be 95% sure of that contains that population value or your sample mean or whatever happens to be that you're evaluating. And so by using that 95% confidence interval, we can determine whether or not we can reject the null hypothesis if that range includes or does not include that population mean. So if your 95% confidence interval of your sample does not include the population mean value, then you can reject the null hypothesis, right? If it does include it, and I'll show you some graphs that kind of illustrate this in a little bit. If they do, if the 95% confidence interval contains the population mean, then you cannot reject that null hypothesis, right? Because there's still, you can still be 95% sure that the values are somewhere in there, and one of them could include that mean. So again, let me show you a picture of that, and it'll make more sense. So this next picture we'll show you is going to be looking at that body temperature data, and we're going to be looking at that smaller sample size. So again, looking at this group, do you think their confidence interval is wider or more narrow than the larger group? Should be wider, right? Because again, it's a smaller sample size, so that's going to increase our confidence interval width. And we already said that that result was non-significant, remember? How it came back like 0.06 or something like that. So it was above our alpha level of 0.05, so it's showing non-significance. So we're going to look at the value, we're going to look at the population mean, and we're going to look at the confidence interval. You'll see that there's going to be some overlap there that shows you that the results are not statistically significant. So again, just remember that when you're calculating your confidence intervals, that remember how we were talking about those t-values and is related to the degrees of freedom you have, and basically that degrees of freedom is just your n minus 1. So as you get a larger population size, notice that your confidence interval number is going to go down, right? So that just means your confidence intervals are getting more and more narrow as your population goes up. So just remember that and keep that in mind when we're looking at the width of those confidence intervals. So again, looking at here, you can see the temperature range on the x-axis. You have your population mean or your null hypothesis being that line kind of going to the top there at 37 degrees centigrade. And then you have your sample mean, your observation mean that was lower than that. But notice the width of the confidence interval and how it includes that 37 degrees centigrade. And so because it includes that, that means that your results are not going to be statistically significant. And so in this case, do I reject or keep the null hypothesis? I keep it, right? Because at this point, because I know that at least some of those values are going to include that population mean, I cannot reject that null hypothesis. So I must say that those two groups, there's no difference between them, okay? That's not to say that I couldn't pull another 12 patients and not see, and maybe those sample would have shown a statistically significant group. But this sample I have right here, it tells me that I cannot reject the null hypothesis just based on this.
You said two groups. Your 12 sample of 12.
Mm-hmm.
And what other group?
Yeah, so in this case, this would be like your sample of 12 versus your population mean, right? Sometimes you're going to be looking at different groups. So if I have like a placebo group and then an experimental group, you could be comparing those means. We'll talk about that in a second, because in some cases, you'll see where we're actually looking at pure values that you could have overlap in. Sometimes you're going to be looking at whether or not the confidence interval crosses 1 or 0 and how that can be tell you significance or not in just a minute. So we'll talk about that in a second. So the next one's going to show that same data set, but instead of using the n of 12, we're going to use that n of 130. And we said that increase in the sample size decreases our standard error of the mean, which means our confidence interval goes down as well. So if you're looking at this, notice that your observed mean is going to be, you see how it's lower than your null hypothesis there, but notice how the confidence interval does not encapsulate any of that null hypothesis mean. So because there's no overlap there, do I reject or accept the null hypothesis? I reject it. I say, get out of here, null hypothesis. You're no good to me anymore. So I can say this group is statistically significantly different than my population mean. Okay. And so if you're looking at the actual literature, you can see that if you were to look at a lot of those values, you don't even have to look at the p-values in a lot of cases. You just have to look at the confidence intervals, and that very frequently will tell you whether or not your results are statistically significant. Yes?
Why is the second box not symmetrical around the observed mean? It's skewed towards the null.
So if you remember looking at, especially with physiologic data, that very infrequently do you have really huge extremes of values, right? So especially with temperature, as you get lower and lower, you're less likely to find results that will go down that far, right? So sometimes you can have confidence intervals that are skewed one way or the other about that. Now certainly standard deviation is always going to be centered around the mean, but sometimes you can have confidence intervals that may be lopsided.
So you have more values that are above that mean? Or
Right, because again, if we're
What
saying
is
that,
the
you know, if we think our population mean is 37 degrees centigrade, you're going to, again, people tend to kind of revert back to the mean, right? People tend to regress back to that mean. So that could be the reason why is that the variation there was kind of skewing more towards that 37.
but this confidence interval, is that not, are the values we got to find the observed mean, is that from that box or is it from a different set of data?
So it's from the 130. If you took all their temperature values
It's
and
not from this 12. Oh, this is.
yeah, this is the end of 130.
Okay.
Yeah. So the box is going to be in regards to the 130. This includes that 12 patients. But again, when you get to smaller population sizes, your standard error of the mean gets bigger, and thus your confidence interval gets wider. Okay, so again, looking at the 95% confidence interval, if it does not contain the value of the null hypothesis, and the result must be statistically significant, or in this case, p of less than 0.05. Okay, if a 95% confidence interval does contain the value of the null hypothesis, then the result must be statistically significant. Okay. So a good rule of thumb to keep in your mind. And so in the examples that we were just looking at, the result represented the comparison of a sample mean with a hypothetical population mean, but this might not always be the case. In a lot of cases, like we mentioned, you might be comparing two different groups together, two different samples, and those are more frequently what you'll find a lot of times in the medical literature, because again, knowing the population mean can be very difficult to do. So that's why you typically are looking at groups. So this rule does work with other types of data. So if we were to look at the confidence interval for differences between means, so say I were to look at the decreases in blood pressure for a type of antihypertensive versus placebo, those would be a difference between the means, and I can look at that. And so basically in that case, if the confidence interval will cross 0, then I know that the results are not statistically significant, right? Because that would show there's no difference from the between the two groups, right? So it should be 0 at that point. There's truly is no difference. So in that case, if the confidence interval is either below or above that and does not contain 0, then you can say yes, p is less than 0.05. It's statistically significant. Another way you can do this as well is if you're looking at proportions. So if you were to look at things like odds ratios and relative risk and things like that, where you're actually comparing proportions of things happening or events between different groups, you can actually use 1 as your cutoff point. Because again, if you were to look at like say risk for mortality, and I was looking at a group of people getting simvastatin versus a group getting nothing, my control group, their risk of having an event occur is say 1 because they're my control. So I set them as my, they have just a 100% chance of the event happening. And then I look at the relative risk or the odds of something occurring in that comparator group. And so in that case, because we're doing proportions, 1 is going to be your center point. And so if the confidence interval contains 1, then it's not significant. You cannot reject the null hypothesis. Again, the supplemental lecture I'll put up will look into that in more detail. Okay, so let's interpret a result that is statistically significant. Let's see what we can pull from that information. So looking at statistical significance only means that the p-value is less than the presented threshold. So whatever our alpha was, just as a p-value is less than that, we can say it's statistically significant. So it means that while the results would be surprising, they're not impossible, right? Because there's still some degree of chance that could have led to that result occurring randomly if I were just to pull from a random sample from that population. So it does not mean that the results are actually interesting enough to report on. You have to look at clinical significance as well to make sure that the results you're finding actually mean anything. So like we said, a 1 degree difference in blood pressure probably is not going to mean a big hill of beans versus if I were to look at, say, a 20 millimeter mercury difference in blood pressure. Like that would be clinically significant if I were to be comparing based on that. So again, just remember to go back to the data and say, even though they found that the p-value is less than 0.000001, does the actual results that they're telling me actually make a hill of bean a difference for my patient? If you can't say yes, then it doesn't really mean that it's clinically significant. So again, a result is statistically significant when the calculated p-value is less than that preset value of alpha that we're going to be setting there. Excuse me. So again, if the temperature of the example mean body was analyzed, does that mean that the mean body temperature differs from that value of 37 degrees centigrade? And again, when we did that sample with 130 patients, we saw that the p-value is very, very tiny. So very, very small chance that was just due to random sampling. And there was a difference between that mean value that we postulated of 37 and the actual group we were looking at. So again, even though the result was significant, if we actually look at the difference in that body temperature, it was very, very small, something like 0.12 degrees centigrade. So again, not clinically very significant for us. So again, we would not really look at those results as anything really astounding. So, and then looking at interpreting results that are not statistically significant. So again, just because something is not statistically significant does not mean that there's no difference between the groups. It just means that the data that we have could not support us rejecting the null hypothesis. And so if there really is a difference there and we don't have the data to show any statistically significant results, what type of error are we making at that point? Type 1 or type 2? So there really is a difference in the groups, but we couldn't show it with the data that we had. Type 2 error, right? So we're making a false negative assumption at that point. And so very frequently that happens when you don't have really a good enough population size to really power your studies. We'll talk about power in just a few minutes. But very frequently it's related to the number of people you have in your study. So obviously a study with an N of 30 is going to be much less likely to be able to show statistically significant results than if you had a sample population of, say, N of 3,000. Right? Unless the actual effect that you're looking at is very, very large, and it's very easy to see the difference between the groups. So again, just because you don't find any difference or any results that are statistically significant does not actually mean that the null hypothesis is true. It's just that you could not reject it based on the data that you have. So again, when you have a large p-value, meaning greater than 0.05, it usually just means that the difference as large as what you observe could happen very frequently just due to random sampling. So like you said, if you had a p-value of 0.8, that means it's very, very easily that the results that you have were just due to random sampling versus there actually being any difference between the groups. So, 80% of the time you'd be able to get a result at least that divergent from your controlled data. So because of that, you can't really reject the null hypothesis just based on that alone. But again, we're not proving the null hypothesis correct, we're just failing to reject it. You guys get the difference between the two? Okay, so a good example of this would be looking at a study back in '93 that was looking at fetal ultrasound. So basically what they were doing here is that they were investigating whether the routine use of prenatal ultrasound would improve perinatal outcome. And so basically what they did, they were randomly dividing two groups of pregnant women. They had one group that received routine ultrasounds twice during pregnancy, and then they had one that only received sonograms only if it was clinically necessary. So then they're looking at the outcomes, including adverse effects and then the morbidity and mortality of both the moms and the babies. And so based on this, what would you say is a null hypothesis?
There's no difference between women who receive all these ultrasounds versus the ones who only get the clinically necessary one.
Exactly. So we're going to say that the null hypothesis is that there's no difference between these groups, that just by getting more ultrasounds, more routine ultrasounds, does not mean you're going to have any difference in morbidity and mortality. Now, in this case, if I were to look at the one tail versus two tail, which one would I use in this case? What do you guys think?
One tail.
You want to use one tail? Which group do you think is going to do better?
The more.
You're gonna do more.
To get more? So these are the kind of assumptions that the researchers have to go into when they are making their hypothesis, right? So they have to decide if they think one group is going to do significantly better than the other, or which one's going to have, say, the higher mean before they can decide whether to do one-tailed versus two-tailed. So in this case, if I had an obvious contender for which one's going to do better, so if I had previous data that showed routine ultrasounds, those patients tend to do better than those that only get them when clinically necessary, then maybe I could say, okay, I'll use a one-tailed test, right? Or if common sense would tell me that more routine ones would do better, then I'm going to do a one-tailed test. But in this case, if I'm not sure, then you would go with a two-tailed test. Absolutely. Which one is going to be less likely to make a type 1 error? Two-tail, right? Because the fact that basically your ability to detect significance would be basically cut in half, because you're looking at either side of that bell curve. Instead of just looking at the 5% on one, you got 2.5% on either end. And so less chance for making a type 1 error with a two-tailed test, but my chance for a type 2 error is going to go up, right? Okay, so again, the null hypothesis here is that the risk of adverse outcomes is identical between the two groups. So there's this term we're going to use called relative risk, okay? So this is going to be the risk of an event occurring in your control group versus your experimental group, and this is going to be a proportion, right? So in looking at your control group, the patients that are only getting it, say, as clinically necessary, your relative risk is 1. That makes sense because they're kind of your baseline, and then your comparator group gets compared to them, okay? So if I were to say, the comparator group came in with a relative risk of 1.2, what does that tell you? Basically, I mean you're 20% more likely if you're in that comparator group to have the event occur, right? And similarly, you could have results that are less than 1 for relative risk, and that would infer that something is protective or it makes the event occur less frequently. So I'll show you an example of that in a second. So here, when we looked at the data, it shows a relative risk of 1.02, and here they did a two-tailed p-value. So do you think that's appropriate? Probably. We kind of talked about why that might be appropriate. So again, so we did a two-tailed p-value of 0.86 and a 95% confidence interval of 0.88 to 1.17. Okay. So in this case, can I reject the null hypothesis based on that result?
Cross over the 1.
Yeah, crosses with 1.
So okay, so good. So if you're looking at the confidence interval, you see that 1.02 with the confidence interval surrounding it goes from 0.88 to 1.17. So that crosses 1 because I'm comparing proportions of means. So yeah, so you would say that's not statistically significant. The other thing is what was the p-value?
0.86.
Yeah, 0.86. So it's well above my 0.05. So I cannot reject that null hypothesis. I cannot show that there is a true difference between this group just looking at this. Now, if you were to look at the range of that confidence interval, what does that 0.88 tell you? So it could be that you'd actually have fewer outcomes, so fewer, say, mortality or whatever it happens to be you're looking at. So it actually could confer a protective effect, right? But then it also can range all the way up to 1.17, which may show that maybe getting more routine ultrasounds is actually harmful, which could also be possible. Who knows? But the fact is that we're just 95% sure that range is going to include our actual true value there. So again, these results are basically just tells us that we cannot reject the null hypothesis in this case. Does not mean that the null hypothesis is true. There could be a true difference there, but maybe there's some other reasons why we cannot show significance with what we're looking at just currently. So we'll talk about why those are in just a second. So again, this is where the data pulled from that we were able to get this. So when you're looking at relative risk, the way you calculate that is if you're looking at the two groups, and you can look at their adverse outcome over the totals, and basically you're going to get a risk of the event occurring, an adverse event occurring, right? So you do the 383 divided by 7,685, and you get that 0.05. And to get relative risk, you basically just divide one by the other, and so that's where that 1.02 came from, right? We'll talk more about relative risk a little bit later. Just know that's how we're basically getting the values there. Okay, so again, looking at how you can approach these results. First one's looking at the confidence interval as it being centered around 1, and it's pretty narrow. So that's kind of just telling us that the data is convincingly show that the routine ultrasound is neither really helpful nor harmful. So again, we cannot reject that null hypothesis. So as far as I can tell, there's really no big difference between the two groups. You could also look at it to say, okay, well, the confidence interval is narrow, but it's not really all that too narrow. So maybe, maybe it makes sense that, by getting more routine ultrasounds, I can help to, guide better direct care or improve outcomes. But the data is not really conclusive at this point. And then again, looking at those ranges of the confidence intervals, in some ways you can interpret as possibly being helpful, maybe even being harmful. But in general, just based on these results itself, you can't really take a lot away from it because they do not achieve statistical significance. So again, you may need to look at other studies. You may need to repeat the data. You may need to run another study in order to help confirm those results or to show something different. You also have to consider maybe there's other outcomes that are beneficial or harmful that you did not actually look at in your study. So looking at things like increased bonding between provider and the patient, looking at early identification and intervention for issues that come up. So again, looking at your study and saying, like, is this actually looking at what I care about versus just saying that the primary outcome was not significantly different. So ways that we can get a more narrow confidence interval, and again, when I look at a result that says it's statistically significant, if it has a really wide-ranging confidence interval, it's really difficult to take a lot away from it, because again, it could be much more extreme or much less extreme than the actual value that they're reporting out. So because of that, it's important to try to get as narrow a confidence interval as you can. And so one of the big ways that we can do that is to reduce the standard deviation. And how do we do that? Increase population, absolutely. So you're looking at a much bigger population in order to help decrease that confidence interval. So again, and just remember that as you increase your sample size by a factor of 4, confidence interval would actually be expected to decrease by a factor of 2. So again, because it's over that square root of the n. So just know that confidence intervals are going to be inversely proportional to your sample size. But very frequently it's hard to get the kind of populations you're looking at. So again, very frequently you'll see that a lot of studies will report out limitations in their articles, and a lot of times they'll say, hey, sample size was definitely a problem. Maybe we're in an area where we could not get enough patients with this, or if you have, say, disease states that happen with rare frequency, that can be another reason why you might have a very small number of patients. So especially if you're looking at like pediatric journals and things like that, you'll find very small sample sizes, because again, the more kind of protected patient groups are harder to get large sample sizes with. So that could be definitely a big limitation to a lot of the data you'll look at. So this is going to feed right into statistical power. So we always want more power, right? Like Tim the Toolman Taylor. Surprised most of you remember that, yeah. I don't think so, Tim. Okay, so the power of a statistical test is the probability that the test is going to reject the null hypothesis when the null hypothesis is actually false, right? So it's our ability to not make a type 2 error, right? So we don't want to get false negatives. We want to actually be able to show a difference if we can. And so we need more power to do that. So again, basically we're just saying here is that as the power increases, the chance of a type 2 error is going to decrease. Typically, you're going to have power being referred to as beta, or the false negative rate. So typically, power is going to be equal to 1 minus your beta. Otherwise, this will be otherwise known as sensitivity. And we'll talk about sensitivity and specificity a little bit later in the course. But just realize that typically, beta is set at 0.2, and so power is typically going to be at 80%. So your beta rate is so very frequently your power calculations will be done with a beta rate of 0.2 or 20%. So you're saying that 20% of the time you could be potentially getting a type 2 error. Because again, you'd rather make a type 2 error than a type 1 error, right? General rule of thumb to remember. So, infrequently do I find actual articles will cite their power calculations, but it's a very important thing that you want to have a good grasp of. So when you do see it, like what does their power calculation actually entail, and what does that mean for you? So power analysis or power calculations can be used to figure out the minimum sample size needed to detect an effect of a given size. Okay, so if you imagine, if I want to find a very small difference between two different groups, do I need a larger patient population or a smaller one? Just like a very minute difference between groups. You probably need a lot of people in order to show the difference there, right? So in order to get to be able to tell a statistically significant difference between two groups for a very small effect size, you need typically a larger patient population. On the other hand, though, if I'm trying to find very huge differences between groups, so say I want to see, if a drug causes a 30% decrease in your blood pressure, that's going to be a lot easier to find, right? Because the result is much bigger. So I would need smaller patient sizes in order to help get that. And that's what my power calculations are doing, is helping you to figure out what kind of sample size do I need in order to find the effect that I'm looking for. And so very frequently, a lot of research is done without any idea of what that effect size is really going to be. So unless you have an idea what that is, it's hard to do the power calculations to figure that out. So and you can also use power to help make comparisons between different types of statistical procedures. And we'll talk about parametric and non-parametric tests a little bit later, but just keep those terms in the back of your mind for right now. So the analogy to understand power, I thought this was pretty good. So say you were to send your child to the basement to find a tool, hopefully not my child. She mainly just drools on stuff right now. But say the kid comes back and says, I didn't find it. It's not there. So what can you conclude? Can you say the tool is there or not?
No.
Probably, maybe it depends on the kid. And the answer is going to be really a probability of whether or not that tool is actually down there in the first place. So what is the probability that the tool is actually in the basement? Or another way to think about it, that if the tool was really in there, so if there actually was a difference between the different groups, what is the chance you actually would have found that difference? What is the chance that kid actually would have found the tool in the first place? Okay, so going back and looking at the different variables that go into our power calculations, you can look at a couple of different things. So one, you want to look at how long did they spend looking for the tool. It was down there for 30 seconds, or were they down there for 30 minutes? And that's going to be analogous to sample size. So again, a larger sample size has a higher power to actually find an effect. Okay. The next thing is, how big is the tool? Don't refer that back to me. Just kidding. So this is going to be analogous to the size of the effect. So are they down there trying to find a buzzsaw, or are they down there trying to find an Allen wrench, right? So the bigger the effect, the easier it is going to be able to find that difference, and thus you're going to need, you won't need as big of a sample size in order to find that, right? And then the other thing would be, how messy is the basement? So this is just referring back to the experimental scatter, or how much variation in the data that you have. Obviously a cleaner basement is easier to find things in, so if you have less scatter, less variability in the data, easier to find those differences when they actually are there. Okay, does that make sense? So you want to have a larger patient population. You want to define the effect size you're actually looking for, and as that effect size gets smaller, you're going to need a larger patient population in order to help find, try to determine that. And that's going to help decrease my type 2 errors that I'm making. Okay. Last thing we'll talk about in this section of slides is going to be testing for equivalence or non-inferiority. Do you guys remember when we talked about bioequivalence back in pharmacodynamics?
Yes.
What does bioequivalence mean?
Different dosages, same effects.
Or same chemical, same effect in the same population of patients.
Yes, but I hear generics.
Generic.
Yes, generics. Yeah, generic drugs is basically what I'm referring back to. So very frequently, in order for when a brand name drug goes off patent, generic manufacturers can come in and produce generics. But what do they need to show to the FDA? Bioequivalence, right? They need to make sure that if I give you the same drug, even though it has a different color, maybe some different inactive ingredients, it still achieves the same blood levels. You guys remember the book that we referred to that tells you the different equivalents? It's the Orange Book. It's a random pharmacy fact. Actually, it used to be a book you'd have that told you whether or not different products were bioequivalent, but nowadays it's just posted online. But they still call it the Orange Book. Anyway, so again, when we're looking at certain types of research goals, we don't necessarily want to see a difference. Sometimes we're looking to show no difference between the groups. Like sometimes we actually want to find there's going to be no difference. And so this would be a case where you want to find out whether the effects of a new treatment are equivalent or, say, non-inferior to a standard. You know, maybe it's a new, more cheap type of therapy, or maybe it has less adverse effects, and so maybe you want to prove that it's non-inferior to the gold standard, so maybe it can become more widely used. And in this case, when we're testing generic drugs, the FDA has some strict guidelines on what they will define as equivalent. And so in this case, you'll see that they will compare peak blood concentrations, and they need to range anywhere between 0.8 to 1.25 times the reference drug, or the brand name drug, right? So who knew that generic drugs has such a wide range they could fit into, right? So I'll show you some graphs to demonstrate this, but they also specified for them specifically that the 90% confidence interval of the ratio should be completely within that range. Okay, so not only do they need to be, the mean blood concentrations should be between 0.8 and 1.25 of the brand name drug, but the whole confidence interval, the 90% CI, needs to be within that range as well. So again, if you were to look at the ratios of the peak concentrations, you can see here that range between 80 to 125%, and then the non-equivalency range is there. So when we look at the next slide, we'll see that the first three drugs we'll be looking at where the mean ratio of peak concentration is within that zone of equivalence we saw there. And so we'll look at drug A that does not prove equivalence. And this is going to be based on the confidence intervals we'll see in a second. But drug B and C are going to be equivalent. So So in this case, you can see that drug A, because its confidence interval is showing that it has a very wide range of peak blood concentrations that you could achieve there. Because it falls outside of that range of 80 to 125%, it's considered not bioequivalent. So you couldn't use that as a generic equivalent to a brand name drug, right? On the other hand, if you look at drug B and C, they do fall within that range. So not only does their mean still fall within the confidence intervals, or the 80 to 125%, but you can also see their whole confidence intervals are in that range as well. So those would be considered bioequivalent. Those would be good to use as generic drugs. And then if you were to look at a couple other ones that have their mean levels outside of that range of equivalence, could you use any of these as generics? No, right? So D is probably kind of inconclusive. Notice how it has very wide confidence intervals. If I could do something to maybe decrease that confidence interval, perhaps my values would be more in line with that 80 to 125%. Who knows? Maybe I need to retest that. But certainly something like F is definitely nowhere even close, right? So that one's, because the confidence interval is pretty narrow, there's probably something about that pill that makes it not bioequivalent, whether it be dosage, the dispersal characteristics, whatever it happens to be. It's different enough where you can say definitely not equivalent. Okay. Okay, so a few questions and answers. Is the p-value the probability that the null hypothesis is true? See lots of heads. No. No. So what is it?
Probability that our value is different from the population.
Yeah, so the chances of the sample mean that you have, the chances of it being as extreme as it is just due to random sampling, right? Just due to random chance. Or basically saying that in order to get a result this extreme, whatever happens to be above or below the mean, this percentage of it could be due to just random chance, okay? So is the p-value the probability that the result was the result of sampling error? Now, sometimes you could have a significant result due to sampling error, but p-value is typically just saying that you're looking for differences between groups, and this is showing you that the chances of this happening are, say 1%. This is 1% maybe due to random chance, but other than that, there's a true difference between these groups here.
Is the answer to this question yes?
So let's see what they put here specifically. They put no still, right? So the p-value is computed assuming the null hypothesis is true and all the differences that result from random sampling, right? So just a little bit more technical terms there. And so then a high p-value proves that the null hypothesis is true. Why is that false?
P-value just shows that the data is not reliable.
So p-value should be below the alpha to show statistical significance. But remember, just because our p-value is large, and it means I cannot reject the null hypothesis, it does not mean that null hypothesis is true, right? Because sometimes you could be going in with a wrong assumption. Say I say that, my null hypothesis is that, 90% of PA students are men. Well, this would obviously be outside of that with you guys. So that would not necessarily say that my null hypothesis is true. It just means that I could have had a bad null hypothesis in the first place, right? So you see that less frequently if you're comparing like actual groups that were derived from a sample population. But if you were to compare a sample to an actual population where you're making an assumption based on that, that's where you can run into issues with that. That make sense? Hopefully, yeah. Okay, can p-values be negative? No, they really only range from 0 to 1, basically. 1 being that the results that you had were 100% due to random chance versus 0 being, or you never really have anything that was 0, but you have very, very small values that say that random chance is very, very unlikely to have proven or to provided those results. And then is a p-value always associated with a null hypothesis? Yep, you need to have a null hypothesis in order to test your data against, otherwise, how do you get a p-value? So, okay, so is it possible to report scientific data without using the word significant? I probably said it about 9,000 times today, so.
Probably not.
You can, right? Because remember, we can use our confidence intervals. We can just look at confidence intervals in the data to show us whether or not you actually need to say the term significant, okay? that's why you should always be very hesitant to believe someone just because they say, oh, my results are statistically significant. You need to look to make sure that, one, the results actually back that up, make sure the confidence intervals actually, because if you look at the medical literature, they very infrequently show you how they actually calculated their p-values, right? But if you can at least look at the confidence intervals, you can look at them and see whether that actually backs up what their results are saying. Okay, and again, very frequently you find that even though a journal is peer-reviewed, you'll find that lots of stuff slips through. So even though they say, hey, this is statistically significant, if it crosses 1 or crosses 0, whatever it happens to be, you'd be like, I'm going to call BS on that one, right? So again, just because something's peer-reviewed does not mean that it's actually been rigorously looked at to your exacting standards. So is the concept of statistical hypothesis testing about making decisions or about making conclusions? If you go back on the slide, you'll see it's more related to actually making like clinical decisions. So based on the data you see, you decide whether or not you can reject the null hypothesis. Can you make decisions about your patients, so whether or not you should start this therapy or not, whatever it happens to be. Are p-value and alpha the same? No, right? So as you mentioned, alpha is more the bar you set for yourself in order to achieve significance. P-values are from the data that you're actually getting from the data itself. Okay. Is p-value the probability of rejecting the null hypothesis? No, it's basically just telling you that these are the probability that these results were due to chance alone. Okay. Any questions on this material? Okay, I'm going to go ahead and actually record section 5 and post that up, so I will expect you guys to watch that for tomorrow, and then on Wednesday we'll have class again, and then Thursday we'll also have in-person class. So I got to keep us on a tight schedule, so please review that video along with the supplemental 4A lecture to be up and ready to go for lecture 6 on Wednesday. Okay? Any questions?
Do you want us to do the exercises in 4A?
So they're not really exercises for you guys to do. It's more like I will be going over some some journal, some results, and kind of applying p-value and some of the stuff we talked about today to that. But just watch that video, watch 5, and then we'll be ready for 6 when you guys come in on Wednesday.
Okay.
Okay? All right. 5 is a shorter one, so don't fret. All right, see you guys next time.